Hi, we are Thursday's Group 1 team in Cal Poly's Aero 304 class. Following a thorough introduction to the low-speed wind tunnel, the students in Cal Poly's Aero 304 class gained a better understanding of proper testing procedure and means of analyzing data. Labs 1 and 2 offered students with the opportunity to run the wind tunnel, while serving as test engineers that collected data to generate concrete deductions. This knowledge served as a foundation going into Lab 3, where more complex flow visualization occurred due to an object placed in the test section. The object in question was a cylinder with pressure ports mapped out along its surface. Although a cylindrical shape is relatively simple, when placed in a flow field it can produce intricate flow regimes. The purpose of this lab focused on how different aspects of the flow, such as Reynolds number, test section walls, friction, and more, can affect the flow around a cylinder. As you can see from the picture displayed, different Reynolds number values will generate different types of flows. At relatively high Reynolds numbers, the phenomenon of vortex shedding will occur. The Reynolds number of the flow around the cylinder directly relates to the separation of the flow from the surface of the cylinder and will be elaborated later. There are two types of drag, which include friction or skin drag and pressure drag. Both these types of drag add up to create a total drag force over the cylinder.
For this particular lab, the team used a cylindrical body placed in the test section of the Cal Poly low-speed wind tunnel in order to observe the effects of the flow over the body of the cylinder. The cylinder being used was 15.24 centimeters in diameter and has 24 pressure ports distributed every 15 degrees evenly over its surface, so pressure data can be obtained from different points along its surface. To effectively see the complex flow visualization of a cylinder in the test section, the use of a smoke machine and a green sheet laser were used to increase the visibility. A viscous flow over an object such as a cylinder will result in the flow no longer sticking to its surface. When this happens, a region of low pressure will reside directly behind the cylinder itself, thus increasing the pressure drag on the body. To solve this problem, the boundary layer can be manipulated. A trip strip or a surface perturbation can be added to the cylinder. This will cause the boundary layer to prematurely transition from laminar flow to turbulent. To do this, a thin sheet of sandpaper, then a wire, was placed at a location before the natural separation location of the flow on the surface of the cylinder. At lower Reynolds numbers, the wire was more effective at delaying separation of the flow. This reduced the pressure drag on the cylinder significantly compared to the sandpaper.
The data collected from running this test involves the understanding and comparison to the theoretical potential flow. The potential flow is defined as the velocity of the flow field described by the gradient of the velocity potential function. It is important to note that using potential flow requires some assumptions to be made. These include assuming the flow is both incompressible and inviscid. By making these assumptions, the equation for velocity potential can be obtained by solving it for the Laplacian. When plotting, certain errors should be taken into consideration since it has a significant effect on the data. Although we did not see any abnormal trends or results in the data, there are soon to be some discrepancies between ports and runs, which are shown in the plots as a standard deviation error bar. In accordance with the methodology of our experiment, 3 tests were performed at 3 different fluid velocities each. These tests include the cylinder with no trip strip, the cylinder with a sandpaper trip strip, and the cylinder with a wire trip strip. Both of the different trip strips were positioned at the same 70-degree angle above the horizontal, which is a direction parallel to that of the free stream velocity, on both the top and the bottom of the cylinder. As expected, the Reynolds number increased with higher velocities. The characteristic length used to calculate Reynolds number was the diameter of the cylinder. Looking at the Reynolds number, the values are different for each test, even though the experiment was run at the same RPM. Even though the values are fairly close to each other, the fact that they are not exactly the same at each test creates error when analyzing the data. Theoretically, the Reynolds number for the 3 different methods tested should be the same. However, and as seen on the table, there are some variations in these values. This is because the velocities for each of the runs were not identical as they should be, so the Reynolds number calculated for each run was done using its specific velocity only. This contributed to some error when the data was analyzed. There is no practical way to get Reynolds number to be exactly the same, therefore an average velocity had to be chosen for each speed.
The results of this data shows several important observations, the most important of which is that the flow is not inviscid. As seen in the plots generated, the theoretical curve of coefficient of pressure of inviscid flow can be seen by the dark blue line and is obtained from the aforementioned potential flow equation. This does not match the data obtained from the untripped and tripped cylinder. This means that the flow coming over the cylinder is separated from the surface and is therefore viscous after this point. This plot was generated for the first test completed at 3.30 meters per second, where the tunnel was run at 100 RPM. In each of the plots, the test without any trip strips, shown by the red line, has the least amount of error compared to when the tests were run with the trip strips. The size of the error bars are very much reflective of this. Looking at this, the team deduced that the placement of the trip strip was a contributing factor. The largest amount of error occurs near where the trip strip was placed at 70 degrees from the flow. Therefore, placement of the trip strip, whether it's covering pressure ports or was misaligned when it was adhered to the cylinder, could greatly affect the pressure recordings at the other plots. The same trend that was seen in the previous plot was also observed when the wind tunnel was run at a faster speed of 11.82 meters per second. The last plot was generated from the data collected at the highest velocity that the team tested at, which was 20.53 meters per second at 500 RPMs. The results are similar to what has been seen in the previous plots and reaffirms the point of viscous flow.
To further analyze the cylinder in question, panel code was used to look at the pressure distribution over its surface. The cross-section of the cylinder is treated as 24 panels with the pressure port located at the center of each panel. With this, a rough estimation of drag can be calculated. By looking at each individual panel, the pressure value in the direction of the flow is drag pressure. Drag pressure can be solved by taking the pressure port value and multiplying it by cosine theta, where theta is the angle at which the pressure port is located. By taking the summation of all the pressure drags and multiplying it by the area of each panel, you can calculate the force of drag. Looking at the following table, using a trip strip changes the force of drag. On average, the force of drag will decrease if the cylinder has a trip strip. This is due to the fact that with the trip strip, flow will stick onto the surface more and will lower the force of drag. Coefficient of drag could also be calculated by dividing force of drag by 1/2 rho v squared times s, where s is the characteristic length of the object, which in this case is the diameter of the cylinder. Looking at the coefficient of drag table, as velocity increases, coefficient of drag decreases for all cases. For the most part, adding a trip strip effectively lowered the coefficient of drag.
Cylinders are everywhere in nature and in man-made objects. The most common example to mention is the trunk of a tree. This is roughly the shape of a cylinder and has to counteract the drag force caused by wind, especially when the tree is tall. Trees are able to trip the boundary layer of the flow by making the surface of the trunk rough, using bark. In doing this, the boundary layer is tripped and the flow stays attached to the trunk for a longer period of time. It is the same concept as adding sandpaper to the cylinder in the wind tunnel. By implementing this, trees need less grounding force to keep them upright and can create less massive root systems, saving valuable energy.
In order to limit error as much as possible, the experiment methodology was followed very closely. A less significant error that affected the data was movement around the lab. Multiple times, people walking around the lab opened doors as well as walked in front of the inlet when the wind tunnel was on. During the first run with the sandpaper trip strip, the strip detached mid-test. The test had to be stopped due to this problem, and all the data relating to the sandpaper trip strip had to be retaken. It was required that the tape did not cover any pressure ports, thus causing some disruption of the flow and probably interfering with some of the pressure ports. There is also the concern that the surface may not be a perfect circle, which may alter the relationship between the potential flow equation and the data collected. With multiple groups testing and placing trip strips on the cylinder, it is likely that it may have been moved or slightly jostled at some point.
The cylinder experiment gave insight into the effects of fluid causes as it moves around an object. To analyze the effects, data regarding pressure was recorded at various locations surrounding the circumference of the cylinder being tested. It is known that the flow moving over the cylinder follows the surface of the cylinder, but at some point the flow separates from its surface. Turbulent flow will then allow the flow to separate at a later point, decreasing the gradient of the low pressure region and in turn decrease the pressure drag on the bodies. The flow on the surface of the cylinder did not mimic an inviscid flow and therefore can be identified as viscous. Given that the flow is viscous, data from the cylinder produced with and without the trip strip was compared. The data showed that each type of trip strip reduces the gradient between the high and low pressure regions.
This cool visualization shows that the flow is not just two-dimensional, but in fact has 3 dimensions in the test section and around the cylinder. Thank you for listening to this presentation. With extra time left during the experiment, the team was able to record a flow visualization with a wire trip strip at a low speed. Check out this cool flow viz that occurred in the test section.